Okay, let's unpack this. We've all seen what large language models can do. The linguistic ability is, it's just incredible.
It really is.
But you always hit this wall, this one fundamental, really frustrating limitation. Their knowledge is completely frozen in time.
It's the time capsule problem. That's a great way to put it. These models, as vast as they are, they know everything,
Yeah.
but only up to the point of their last big training run.
Right. So if you ask them about something that happened yesterday,
Or, and this is crucial for businesses, if you ask about your company's latest policy update, they're just completely blind.
and they either say, I don't know, or even worse, they start making things up.
That's the hallucination we hear so much about, is just filling in the gaps with plausible-sounding nonsense.
And the knee-jerk solution you always hear is, oh, just train the LLM again.
But our sources really highlight how completely impractical that is.
It's not just the cost, which is astronomical. We're talking millions.
It's the time. It can take weeks, even months, to retrain one of these huge models, which completely defeats the purpose of having real-time knowledge in the first place.
So just not a scalable solution for the speed of information today.
Not at all. And that brings us to our mission for this deep dive, to really understand the ingenious workaround that solves this problem.
Retrieval Augmented Generation.
Or ARGI for short.
ARGI. It's such a great acronym because it really tells you the whole story. You have retrieval,
Which is accessing knowledge from some external source, like your own document library.
then augmented, meaning you're enhancing the LLM's process with that specific context.
And finally, generation. That's just the model producing the final coherent text based on the facts you just gave it.
So our goal here is to show you not just what ARG is, but the precise step-by-step workflow, including the critical role of something called chunking.
And we'll get into how the most advanced ARGI architectures are actively fighting those hallucinations to give you accurate, grounded, and actually relevant responses.
Okay, so if RAG is basically giving the LLM an external brain, where does that brain store all its knowledge?
That's where we meet the foundational component, the vector database.
It's that vector database.
It's the dedicated storage layer for RAG's retrieval step. And it doesn't store data, text, images, whatever, as raw files.
It does something different.
It transforms everything into these numerical representations called embeddings.
Okay, embeddings. We have to pause here because this feels like the real magic ingredient. How can a string of numbers actually capture the meaning of a piece of text?
Well, a machine learning model, an embedding model, converts the data into these high-dimensional vectors. The key idea is that the models are trained to capture semantic meaning through distance.
Meaning things that are conceptually similar are placed closer together in this huge digital space.
Exactly. Imagine a giant map. All the embeddings for concepts related to, say, medicine, cardiology, immunology, they'll all cluster together in one corner.
And concepts about space travel would be somewhere else entirely.
In a distant corner, yes. So if you then add a new concept, like telemetry data, its vector will naturally land closer to that space travel cluster. The vector space understands semantic relationships, not just keywords.
That's the core takeaway, isn't it? When I search the system, it's not looking for keyword matches like an old-school database. It's looking for the idea I expressed.
Which is why RAG is so powerful. It uses this reliable, retrieved information to make sure the LLM's response is grounded in actual context. And it does this without ever needing to retrain the core LLM itself.
We're just using the LLM for what it's best at, language.
It's incredible language and reasoning skills, exactly.
All right, let's pull back the curtain and look at the actual workflow. Our sources break this down into two main phases, indexing and then query execution.
Phase one is all preparation. You're building that knowledge base. And the very first step, which is so important, is chunking.
So breaking documents down, help me understand what happens if you do this badly. What's the real danger of not chunking your documents correctly?
The danger is that the embedding for that, say, 100-page document becomes way too broad, too generic.
It's meaningless.
Pretty much. If a vital piece of information is buried on page 37, the single vector for the whole PDF is useless because it just points vaguely to the entire thing, not the specific fact you need.
Poor chunking means poor retrieval. Guaranteed.
Guaranteed.
Okay, so we break the text into useful chunks. What's step two?
Step two is generating embeddings. You use an embedding model, often called a biencoder, to turn those chunks into vectors.
And step 3 is store in the vector database. So now these vectors are indexed, they're stored, and this database is basically the RB application's long-term memory.
And it's important to note the original text and metadata are stored right alongside the vectors.
Right. So that brings us to phase 2, which kicks in when a user actually asks a question.
Step 4, the user input query. Simple enough.
Step 5, embed the query. And this is crucial. You use the same embedding model that you used in phase 1.
You have to. It keeps the whole semantic space consistent. Then step 6, the heart of retrieval. Retrieve similar chunks.
This is where the query vector is compared against all the stored vectors.
Using something called approximate nearest neighbor search, or ANN, to find the most similar chunks.
Wait, I have to stop you there. Why approximate?
Right.
If we want factual grounding, shouldn't we demand the exact nearest neighbor?
That's a fantastic question, and it's a key engineering trade-off for scalable AI.
It's about speed.
It's all about speed. If you had a database with billions of entries, doing an exact search would be computationally impossible. It would take way too long for a real-time answer. ANN algorithms are lightning fast and give you results that are, for all practical purposes, just as good.
Unnecessary trade-off. Okay, now let's talk about step 7, re-ranking. This seems to be where the advanced systems really shine.
They do. A bioencoder is fast, great for that initial retrieval of, say, 50 chunks. But for accuracy, you want a second, more powerful model that's usually a cross-encoder.
So the cross-encoder is slower but smarter.
Much smarter. It's designed to specifically evaluate the relationship between the original query and each of those 50 chunks, one by one. It then assigns a relevance score to prioritize only the absolute best information.
So the bioencoder is the fast filter, the cross-encoder is the precise editor, and finally, step 8 is generate the final response.
Right. The LLM gets a prompt that combines the user's original question with those top-ranked, highly relevant context chunks.
And because it has that context right in front of it, it can generate a coherent, fact-based answer, which dramatically reduces the chance of it hallucinating.
It's essentially reading the answer right before it speaks.
Okay, we have to go back to that first step again. Chunking. The decision you make here really determines everything that follows.
It does. Our sources lay out 5 core strategies. The simplest is fixed-size chunking.
Just splitting the text by a set number of characters or tokens?
Exactly. It's simple, great for batch processing. The big downside, though, is that it can just chop a sentence or an idea right in half.
Disrupting the meaning.
Totally. The practical fix, if you use this method, is to maintain some overlap between the chunks to try and catch those broken ideas.
Okay, moving up in complexity, there's semantic chunking.
This is much smarter. It segments the document based on meaningful units, like sentences or paragraphs. You group sentences together as long as their meaning, their cosine similarity, stays high.
And when the similarity drops off a cliff?
That's your new chunk. It preserves complete ideas, making retrieval much more accurate. The tricky part is defining the right similarity threshold.
Right, which would be different for a legal document versus a creative story.
Absolutely. Next up is recursive chunking. It tries to find a middle ground. It first looks for natural separators, paragraphs, headers.
And if a chunk is still too big,
It recursively splits that chunk down further until it fixes the size limit. It maintains the flow, but, adds a bit more complexity.
okay, method 4 is document structure-based chunking. This uses the document's own formatting, like titles and headings, to define the chunks.
This is great for, say, a well-structured manual. But it assumes the document has a clear structure, and those chunks might still be too long, so you might need to combine it with recursive splitting.
And finally, the most advanced but also the most expensive, LLM-based chunking.
Here, you're literally asking the LLM itself to break down the document into semantically complete chunks.
It would have the best understanding of context.
By far, it gives you the highest semantic accuracy, but it's the most computationally demanding because you're making multiple calls to the LLM, which costs time and money.
That's a great breakdown. So once you know you need to adapt an LLM, how do you decide between RYAG or fine-tuning or just simple prompt engineering?
Our sources have a great way of thinking about this. It boils down to 2 questions. How much external knowledge do you need, and how much model adaptation do you need?
Adaptation being like changing the model's writing style or teaching it new jargon.
Exactly. So if you have low knowledge needs and low adaptation needs, you just use prompt engineering. It's the cheapest, easiest approach.
But if you need high adaptation, like teaching the model your company's unique vocabulary and tone, but you don't need a lot of external data,
Then fine-tuning is your path. You're actually adjusting the model's internal weights. high upfront cost, but it pays off if you need that specific personality.
And our egg, our hero for today, lives in the quadrant of high external knowledge but low adaptation.
That's its sweet spot. You want the LLM to use your custom knowledge base, but you don't need to change its core behavior. It's much cheaper and faster than fine-tuning.
And what if you need both?
If you need a custom knowledge base and a change in the model's behavior, that's when you go for the hybrid RAG plus fine-tuning approach.
It's a really clean way to frame that decision.
It is. It forces you to weigh the cost of tokens versus the cost of training.
Okay, let's talk about the cutting edge, because the simple retrieve then generate flow we described, naive RG, it has its limits.
It does. It can struggle with complex multi-step questions where one piece of information depends on another.
Which has led to some incredibly creative, advanced architectures. Let's start with HIDE. That's hypothetical document embedding.
Right. The core problem HIDE solves is that a user's question is often semantically very different from its answer. A short question might retrieve documents that are way too broad.
Because the query vector is just too far away from the detailed answer vector in that semantic space. So what's the trick?
The trick is to use the LLM first to generate a hypothetical answer. It might be imperfect, it might even have some hallucinations.
But that's okay.
It's okay, because the embedding of that detailed hypothetical answer is semantically much closer to the real documents than the original short question was.
That is brilliant. So you're generating a best guess answer just to get a better semantic footprint to search with.
Exactly. You search with the hypothetical answers vector, retrieve the real documents, and then use those real documents to generate the final corrected response.
It's like building a better search query on the fly.
It is. And another huge innovation is agentic RAG. This is where we stop thinking of RAG as a static pipeline and start introducing planning and self-correction.
It sounds like giving the system autonomy to think for itself.
In a way, yes. An agent might look at a complex query and decide to first rewrite it to be clearer. Then another agent might decide if it needs multiple sources, not just the vector DB, but maybe a live API call or web search.
And what if the answer it finds is weak?
That's the critical loop. A final agent checks the answer's relevance. If it's not good enough, the process loops back. The agent might reformulate the query, try different sources, or synthesize the information differently.
So it can handle multi-step reasoning that naive RAG just can't touch.
Precisely. It adds a layer of robustness.
But all this complex retrieval, it can be slow. Which brings us to an optimization from Meta AI called refrag.
Refrag is all about efficiency. Naive RAG often stuffs the LLM's context window with a ton of irrelevant text, which costs time, money, and compute.
So refrag tackles that with two big ideas,
Yeah.
chunk compression and a relevance policy.
Yes. And that policy is trained with reinforcement learning to be incredibly selective.
How does it work?
Every retrieved chunk is first compressed into a single, dense embedding. The relevance policy then looks at these compressed embeddings and decides which handful are truly the most relevant.
So instead of passing 50 full-size chunks to the LLM,
The system only expands the top, say 5 or 10 chunks back to their full text and includes only those in the final prompt.
and the impact is huge.
Astounding. Our sources say refrag gives you a 30 times faster time to first token
30 times.
and effectively a 16 times larger context window with no loss in accuracy. You're processing 16 times the context at 30 times the speed just by being smarter about what you show the model.
That's genuinely a breakthrough. So what does this all mean when you zoom out?
It means RAG is the bridge. It's the seamless link that grounds the amazing language skills of LLMs with specific, up-to-date, accurate information from your own data. It solves the knowledge cutoff problem without the insane cost of retraining.
And here's what I find really interesting for the future. This shift we're seeing from naive RE to these more advanced agentic systems, it tells us something profound.
What's that?
The future of these systems isn't just about knowing information. It's about actively reasoning and dynamically planning how to go find it.
Absolutely. They're becoming less like static encyclopedias.
And more like intelligent, active researchers. The next time you ask a chatbot a really complex question, just consider that you might not be talking to a frozen piece of software. You might be talking to a research coordinator that is dynamically pulling resources from all over just for you, something to mull over until our next deep dive.